Hi students, today we're learning about the limit of a function, and I'm actually going to be doing it right in words for the first time, so hopefully this works. So we've talked about what a limit is in class, and we've watched some videos or done some exercises to kind of get you thinking about what a limit is. So this note now will formalize what notation you're supposed to use when defining a limit, and also exactly what vocabulary you should use when you're defining what a limit is. So the limit of a function, if it exists, because as we all know, the limit does not always exist. So for some x value, which we'll just call a, let a be any specific x value, the limit is the height or the y value that the function gets closer and closer to as x gets closer and closer to that value of a from either direction. So this seems a kind of bit arbitrary. So you can draw this function here. So then let's choose some value a. So let's just say it's here. So this is the point we're trying to get to. So let's say this corresponds to the x value of a. And so then you have f at a. But when we're looking at the limit, we actually don't care about f at a, which is a little bit hard to wrap your head around. But just imagine as the function gets closer and closer to a from the left and closer to a from the right, so as x gets closer and closer, what y value is this function getting closer and closer to? So that is the limit. That should be a straight line. This is a bit difficult. So notice in this case, the limit is the same as f at a, but that's because this is a continuous function. You'll see soon enough that that's not always the case. So you're saying as you're getting closer and closer to the x value that you want, what is the y value getting closer and closer to? Okay, so the notation here is the limit. So we say that LIM is the limit as x approaches a. So limit as x approaches a of f at x is equal to whatever it is. So we'll call it uppercase L for now. So this is the limit of f at x as x approaches a equals L. That's how we would say it in words. Okay. So a more formal explanation is that the value of f at x can be made arbitrarily close to L by choosing x sufficiently close to a but not equal to a. So for example, the expression the limit as x approaches 2 of 3x plus 1 equals 7 means as x gets closer and closer to 2 from the left and from the right, f at x gets closer and closer to 7. So you might be thinking, Mrs. Wiens, duh, just put 2 into this formula and you get 3 times 2 plus 1 is 7. Why do we need all this limit business? Well, we can only plug in x equals 2 because this function is continuous, but lots of functions have holes. So let's take a look at an example where a function has a hole. So for example, let's take, that's too bright. Let's take this example, okay? So just create, with the ruler, a straight line here. And just put a hole in the middle and continue the line. So we can put arrows on this end. And then right above the hole, put a dot up here. Okay? So we'll call this f at x for the purposes of this example. And we'll say that this hole is happening at an x value that we will just call a. And we'll say that this y value is 5. And this y value is 8. So why am I showing you this example? Well, the value of f at a is not important. So notice here that f at a is actually equal to 8. Because if you put a into this value, this solid dot represents what the function is equal to at a. However, the limit is actually equal to 5. So the limit as x approaches a of f at x is equal to 5 because the limit doesn't care about what actually is happening at a. The limit only cares about what's happening on either side of a. Okay, just a moment.